This is David Van Vranken here at UC Irvine. This is the 8th lecture during week 3 of the spring quarter in 2020 at UC Irvine. This is the quarter of remote instruction on the UCI campus caused by the coronavirus. I saw this article on a mining disaster in a coal mine in Tennessee at the turn of last century in the town of Fraterville. A really harrowing account of over 200 men and boys who were trapped in this mine by an explosion. Most of them died immediately, but some slowly ran out of oxygen and suffocated to death and had enough time to pen letters to their loved ones, really pulling on the heartstrings there. And they're talking about how they're running out of air in these notes. And it's really poignant. And in one of these letters, the man is saying, "Oh God, for one more breath." Really sad. And I think it's important to be present to the plight of these miners, many of them younger than the people in this class. But I wanted to take time and talk about some organic chemistry here, because there is organic chemistry in this really sorrowful tale. If you'll note, on the tops of the miners' caps, they're wearing these devices called carbide lamps, and there's organic chemistry there that we can learn from in this instance. And so let's go ahead and talk about these carbide lamps. The miners were wearing these lamps on their heads that use a compound called calcium carbide. So it looks basically like gray rocks. You can grind it up. And they put that in the bottom chamber of these metal carbide lamps, and then they slowly drip water. There's a controlled drip of water under this carbide, and the water reacts to generate acetylene gas, and that burns. Let's take a look at the chemistry behind that. I've drawn a Lewis structure, one of many possible Lewis depictions of calcium carbide, where it's basically acetylene, but instead of H's at the end, you have bonds to calcium metal. These types of compounds are very much like the sodium acetylide reagents that you learned how to generate in chapter 11 of our Smith textbook, and that we've been talking about in chapter 20 for additions to carbonyls. If you generate these types of sodium acetylides using sodium amide in the laboratory, you jealously guard these reagents so that you can add them to carbonyls. You don't allow them to come into contact with water, because if you allow these types of reagents to come into contact with water, whether it's sodium acetylide or a calcium carbide, it will rapidly deprotonate. And so the reaction of these calcium carbon bonds, very basic, with water, puts protons on the ends of these. And if you do that twice, you end up generating acetylene gas. And of course, that mixes with air in the presence of an ignition source to generate a constant flame as you generate acetylene gas. And this is what was lighting the way for those miners. And they had to make the difficult choice of whether to keep their lamps on and then run out of oxygen, or to turn their lamps off and use that oxygen for their last gasp of breath. They probably turned their lamps off and died in the darkness. That's very sad. But it's a great chance for us to reinforce some of our concepts that we're learning about organometallic reagents and the reactions with water. Again, we're here in chapter 20 talking about the addition of organolithiums and organomagnesium reagents to carbonyl compounds. And on Monday, we talked about silyl ether protecting groups for protecting OHs so that they wouldn't destroy these valuable reagents that we've been working with. And now we're going to talk about the addition of organolithium and organomagnesium reagents to esters. And and this is a particularly important pattern of reactivity to remember. I could pick any ester that I wanted. I'm going to pick one attached to a cyclobutane ring. Maybe it'll make it a little more interesting. I'm not sure. And what we're going to do is we're going to envision what would happen if we took phenolithium. It's got a nucleophilic phenyl-lithium bond in there, and we added it to this carbonyl. That carbon-lithium bond in phenolithium is so nucleophilic, it will immediately add. And we'll follow this up by adding it by doing a water workup on that reaction. Now, when we do this, you can't just use, and I'll explain why shortly, one equivalent of phenolithium. We have to add, if we're adding to an ester, 2 equivalents of our alkylithium or of our Grignard reagent. That's absolutely essential. And when you do that, when you follow that recipe for esters, doesn't matter whether it's a methyl ester or a phenyl ester or an ethyl ester, you have to add 2 equivalents. You end up adding twice to that carbonyl. So we don't add 1 phenyl group, we add 2 phenyl groups. And now that oxygen atom that used to be attached there has now disappeared. We don't usually draw this, but if I ask you to draw the products, I would expect you to draw all the products that contain carbon. And so ethanol is the other product of that reaction. But certainly if you're doing this reaction in the lab, you're not interested in isolating the ethanol. You would simply evaporate that with your solvent and isolate this new alcohol with the carbon-carbon bonds. It's the compound with the new carbon-carbon bonds that we're invariably interested in. Let me take another example. This one is a little bit strange because this substrate for the reaction, the reactant here, is so low in molecular weight and is so small. But just to show you that we can apply the same principle using Grignard reagents. So in this case, if we use 2 equivalents of ethyl magnesium chloride, doesn't matter whether it's ethyl magnesium bromide or ethyl magnesium chloride. I'll write 2 equivalents here. And then we'll follow this up with a water workup. And the products of this reaction, one product that we get is, of course, the isopropanol. That's our leaving group. That gets protonated by the water. We just swamp it with a ton of water. But the other product now has 2 ethyls added to this carbonyl. So we still have the carbonyl, and there's the OH you get, and there's now 2 ethyl groups that are added. And that's the pattern of reactivity that you need to practice with, that you need to memorize. That with esters, you add 2 equivalents of the organometallic reagent. You have to write 2 equivalents. Sometimes you can write the numeral 2 in front of the organometallic, and I'll know that that means double the normal stoichiometry. I like to add 2 equiv. Equiv is the ACS, American Chemical Society abbreviation for equivalence. We don't use EQ, that means equation. All right, let's go ahead and take a look at what's going on in those reactions. Why is it that you can't just add 1 equivalent, even if you wanted to, and stop at the ketone stage? That turns out to be a real pain, actually, because sometimes you want the ketone. So let's go ahead and take a look at what's going on mechanistically with this reaction. So if I take some sort of an ester and I add an organometallic reagent, like that ethyl magnesium chloride, there's that nucleophilic bond. I guess I didn't draw the carbon atom, but there's a nucleophilic bond there. And that nucleophilic bond will attack this carbonyl, no question about that. So favorable to attack carbonyls with these powerful reagents. Great, great reactions, unlike SN2 type processes. And so when we add to this carbonyl, we'll generate an alkoxide anion. And we've kind of already seen this with hydrido group addition, that when you have alkoxide anions directly next to O-alkyl leaving groups, you cannot isolate these species, you cannot stop these OR groups from being pushed out, right? Again, if you've got some bad memory about, oh, you're not allowed to use alkoxides or hydroxide as leaving groups, that's nonsense. That's only for SN2 reactions that they're not leaving groups. But when you have this great nucleophile right next door, you can't stop that from acting as a leaving group. So let's go ahead and watch the product of this is going to be a ketone. And so after you eject the alkoxide, we now have a ketone. And this ketone will be more reactive than the ester you started with. We're going to talk more about this in a couple of chapters where we go into great detail talking about the chemical reactivity of esters, of carboxylic acids. We'll find out later in a couple of chapters that the lone pairs on that oxygen are deactivating that carbonyl. And once you have a different substituent with no lone pairs, the ketone's more reactive. You cannot stop. There's no way to stop any additional molecules of ethyl magnesium chloride, your nucleophile. You can't stop those from adding to the ketone before they add to the ester. And so you can't stop that second addition. You can't just write the word 1 equivalent and get a good yield of the ketone in this reaction, because after you've added half of your reagent, the other half will add preferentially to the ketone. So you have to add 2 equivalents of the Grignard reagent to get a good yield. or the alkylithium reagent to get a good yield. That's required here. And so there's no way to get a good yield of the ketone. And so you end up adding 2 equivalents of your nucleophile in this case. And we'll have magnesium chloride, chloromagnesium cation floating around. And the other component that you got floating around, which is not really interesting, is the leaving group as the salt. So those are sitting there at the end of the reaction. And then you finally come back in with your aqueous workup, and you just swamp this with a ton of water. So you've got a ton of water in there, and that simply protonates your alkoxide so that you can isolate a nice neutral molecule. That's what all organic chemists want to isolate, neutral molecules, if they have a choice, because you can extract neutral molecules into organic solvents and then evaporate the solvent. That's really our goal here. And the same thing is happening to your alkoxide leaving group. That's significantly less interesting. Again, your alkoxide leaving group is also getting protonated by water. So just in case you're wondering what happened in that reaction, this is, right, that's getting protonated. And so you'll end up isolating both of these alcohols as the products of the reaction. So when you add to esters with Grignard reagents, with alkylithiums, doesn't matter whether it's ethyl magnesium chloride, phenyl magnesium bromide, or an alkynyl sodium species, you can't stop with one addition. You have to add two equivalents, and you're going to get double addition whether you want it or not. And you won't get a good yield unless you add 2 equivalents. Okay, that's a super important pattern of reactivity. And I'm sure every single section of organic chemistry here at UC Irvine and other schools, they'll ask that kind of question on exams. That's exactly the kind of thing that they expect you to know after you've learned about the reactivity of alkylithium reagents and Grignard reagents. I'm not sure if they still do that. That used to be a standard lab, was to take an ester of benzoic acid and do a double Grignard addition. Not sure if they still do that in the 51L lab series. Okay, let's go ahead and take another, a very addition of alkylithiums and Grignard reagents to a very special type of carbonyl compound, and that's carbon dioxide. Let me go ahead and draw the Lewis structure for carbon dioxide here. That's the Lewis structure for carbon dioxide. It's almost like 2 carbonyls on 1 carbon atom. And so you can add a Grignard reagent or an alkylithium will add to carbon dioxide. So if you have some compound with a nucleophilic bond, like a carbon magnesium bond, a carbon lithium bond, we can now add carbon dioxide to this. How do we do this? We have dry ice in our laboratory, so frozen carbon dioxide. That's what we use to cool down a lot of our reactions to -78 degrees. So when I write CO2, we're usually not bubbling in gaseous CO2. Oftentimes you just throw in a chunk of dry ice, and usually you're not worried about having excess in there. Now in these reactions, you're going to get an anion in this reaction after it adds to the CO2. Once you add to the CO2 and push the electrons up to oxygen, and we have to protonate these, but the challenge here is we can't just protonate it with water like all the other reactions I've showed you. So here, maybe I'll be a little bit more explicit. We have to work this up using hydrochloric acid or some strong acid, not a weak acid. We have to use a strong acid to protonate the product because we want to isolate neutral molecules. We don't want to isolate the carboxylate salt. We want to have that with a proton on there so it's neutral. Let me go ahead and talk about the mechanism for the reaction, the arrow pushing mechanism, and we'll talk about why it is that you have to use aqueous HCl. You can't write water. If you write water to get that product, I'll count that wrong. That's not right. So let's go ahead and see what's happening here. I'll go ahead and draw this nucleophilic bond to magnesium. There it is. And then we'll draw our carbon dioxide electrophile there. And so the bond is nucleophilic. It's going to add in to the carbonyl, just like that. So you'll make a carbon-carbon bond. Love it. And so now we've got this carboxylate anion. I guess there's 3 lone pairs. Let me draw all of those. And there's going to be a a bromomagnesium salt that's just floating around here. And now when you work this up using an aqueous workup, you can't just use water. Water is not acidic enough to protonate a carboxylate. The difference in acidity that you need an acid that's at least 11 orders of magnitude more acidic than just plain water. And so that's why we have to switch to a strongly acidic solution like aqueous HCl. And so I'm not going to draw out I guess I can write the HCl here, but it could be H3O. Let me not worry about that. I'll just write HA, because we don't know when you use aqueous HCl whether it's H3O plus that's protonating it, whether it's HCl that's protonating it. Doesn't matter. Mechanistically, we just have some acidic species, not just water, but an acidic species like hydronium or HCl that's protonating that carboxylic acid, and that's what's leading to the carboxylic acid product that's neutral and that we can extract into an organic solvent. Okay, that's addition of Grignard reagents. It's the same with an alkylithium. If you took phenylithium or ethyl lithium or butyllithium or any other nucleophilic reagent, you can make bonds directly to form carboxylic acids in one step. Okay, we're going to kind of switch away from organolithium reagents and organomagnesium reagents. And let's go ahead and talk about a different class of reagents that has a kind of a different utility or a different selectivity. So I'm going to draw in the middle here one type of substrate. And then we'll talk about two different reactions, one to the left and one to the right. And here's kind of the key features of this. I'll make this a ketone, but there's really 4 atoms here that matter. So I've got a carbonyl group, and this position next to the carbonyl, either of these positions, but I'm going to point to this, we oftentimes label those with Greek letters, alpha. The position that's alpha to the carbonyl is either of these 2 carbons, and one further away we refer to that as beta. And you'll see similar nomenclature used for amino acid chemistry when they talk about, beta-branched amino acids. It has to do with the distance away from the carbonyl. So we would refer to this as an alpha-beta unsaturated enone. It tells us that the double bond is at the alpha and beta positions, not beta and gamma, not gamma and delta, but alpha and beta. And these are conjugated. These 2 double bonds are conjugated with each other. And we can draw resonance structures to explain that if we wanted to. Now, when we add a nucleophilic reagent like an alkyl-lithium reagent, you get exactly the pattern of reactivity that we've been talking about throughout this whole chapter. So if you had a Grignard reagent, if you had an alkyl-lithium reagent, that carbon-lithium will add across the OH, and if we follow this up with an aqueous workup, like we've been doing, then we'll end up with an alcohol product, and it'll have this new bond where the R group is added, and the water workup will add a proton. So we end up adding R and H across that carbonyl bond with this 2-step combination. But there's another reaction that they introduce in section 20.15, and that's the addition of a class of reagents called cuprates. First, I'll write it out as kind of a text formula, and then I'll draw the structure a little bit lower so we can understand more clearly what that cuprate is all about. So the cuprate reagent can be lithium diethyl cuprate, lithium dimethyl cuprate, lithium diphenyl cuprate. Just assume that you can make those reagents. If you can make an organolithium and an organomagnesium reagent, then you can make those same R groups attached to a cuprate. And we also follow these up. Let me go ahead and draw out the formula here. So anytime, if you can just assume you can get your hands on any cuprate reagent where R is something you could have made. If you can make an alkyl lithium and an organomagnesium species, you can also make the cuprate. And then we also follow these up with a water workup in those cases as well. And the pattern of reactivity is that the alkyl group that gets transferred adds not to the carbonyl carbon, but it adds to the beta carbon. Let me go ahead and draw that. And the H that gets added ends up getting added over here to the to the alpha carbon. And so this is the pattern of reactivity that you get. You can see that the H from the water workup ends up over here and the R ends up over here. And they refer to this, some people like to number this system instead of using alpha and beta. Some people like to enumerate these enone systems 1, 2, 3, 4. So they'll refer to this, and I might make a mistake and refer to this as 1,2 addition. If you want to add 1,2 across this 4-atom system, then you just use a regular alkylithium reagent or a Grignard reagent. If you want to add to the 4th atom in this system, 1, 2, 3, 4, then you use a cuprate. And we refer to this as 1,4 addition. And I'll try to explain the meaning behind that 1,4 addition in just a moment. Let's go ahead and take a look at the mechanism. And it's going to require us to draw out the Lewis structure for this cuprate reagent. So here's the structure for that cuprate reagent. So what's key to this cuprate reagent is that we have 2 bonds to copper, right? If you just have 1 bond to copper, there's no negative charge. It's an alkyl copper species. But when you add a second carbanion, ethyl anion, phenyl anion to the copper, it takes on a negative charge, and we refer to that as a cuprate. That 8, the suffix 8, cuprate, tells me there's a negative charge on copper, and it tells me that all the lone pairs and all the bonds to that copper are nucleophilic. I don't see any lone pairs, but I see bonds. Those bonds are nucleophiles. So when we draw out this enone system, this alpha beta unsaturated enone system, it turns out that this is reactive with some electrophiles at the beta position. And so let's go ahead and take these nucleophilic bonds, and instead of attacking carbonyls, that's not what cuprates do, we're going to attack right here at the end, at the beta carbon of the enone system. And so when we add that, we're going to push the electrons all the way over here to the oxygen. That's satisfying, right? Oxygen is electronegative. That's kind of the way we draw out additions to carbonyls. And so we're going to generate a type of intermediate that may look a little bit weird to you now. I promise you, by the end of chapter 24, these things will be like, I don't know, they will be so unbelievably familiar to you. And you can say, hey, I saw it here for the first time back in chapter 20. We refer to these as enolates. Remember that name. Because when we come back to these species in a couple of chapters, we're going to be using this carbon over here as a nucleophile all the time. It helps to draw enolates, not by this structure. This is the best resonance structure, by the second best resonance structure. Let's go ahead and take these electrons over here in the enolate and push them over to carbon. That's not as good as the resonance structure here, but it's going to tell me about what pattern of reactivity I should expect. I think I'm forgetting this R group over here, so let me draw that R group that we just added as a bond. And so when I draw this resonance structure, I'm going to end up putting a negative charge in a carbanion over here, alpha to the carbonyl. So this is really the resonance structure that's important. When you swamp this with water, these are the same molecule, just different depictions. When you swamp this with water in your aqueous workup, it's the alpha carbon that's getting protonated and picking up the proton to make the stable product in the reaction. And so this is the mechanism for generation of that alkyl group. Okay, in this book, there's 2 sections toward the end of the book that really are just review. They're reviewing additions of organolithium reagents and organomagnesium reagents, and maybe how to prepare substrates for those reactions. And you should go back and read those. I'm saying I'm not going to take the time to redraw it on slides. It's a review of all the stuff that we've already covered, but I expect you to go back and review those. This is such an important chapter. Work every single problem in the chapter, every single problem in the sapling homework, because that's going to be critical for this chapter. Let's go ahead and do our own kind of mini review here and talk about what are some of the common themes, the important themes for this chapter. Forming carbon-carbon bonds by adding to carbonyls. That's the theme for this chapter. It's such an important theme. It's such an important topic for organic synthesis. So one of the reactions that you would have already learned back in chapter 12 of the 5th edition of the Smith textbook would have been let me go ahead and take allyl alcohol as an example. The oxidation of alcohols to aldehydes and ketones. If it's a primary alcohol, you get an aldehyde. And that is such an important reaction if you're using, after you learn about organolithium and Grignard and Grignard reagents, organomagnesium reagents, because now that you've converted your alcohol into a carbonyl, now you can make bonds to that. You can add alkyl lithiums, you can add organomagnesium reagents. Let's go ahead and take methyl lithium, such a simple compound. It's got a carbon lithium bond in there, and we'll follow that by working that up with water. It's an aqueous workup. And so once you know how to take alcohols, if you wanted to form a carbon-carbon bond here, you have to oxidize it up first, then you form a carbon-carbon bond. And that brings you back to the alcohol stage. And if I do this, I'll end up with 2 enantiomers. Let me recognize that I just generated a stereogenic center. I'll make the methyl group wedged. There it is. I could have drawn the OH wedge. The point is you get a mixture of 2 enantiomers in that reaction. So we end up with this, right? If the point is, if I want to make a carbon-carbon bond with this alcohol compound, I first oxidize it to an aldehyde using PCC, and then I do my addition. If you didn't remember this PCC reaction, you would be completely lost about how to make a carbon-carbon bond here, because there's 2 H's on that, what's called the carbonyl carbon. Now, once you've done this, you can do this reaction again, this sequence again. If I want to make another bond next to this carbonyl, and it doesn't matter whether I've got the R or the S enantiomer, the stereogenic center, I can oxidize it again with PCC. And now I'm set up again. Look at that, how amazing that is. That sequence of PCC followed by an organometallic addition is super powerful. It allows you to take alcohols and form additional carbon-carbon bonds if you first oxidize them up using PCC. So you add phenolithium, for example, or some other, whatever Grignard, or you wouldn't make sense to add a hydrido reagent, because that, like sodium borohydride or lithium aluminum hydride, that would take you right back. That doesn't make any sense to do that. But you can form carbon-carbon bonds to that so easily. And there we go. And this, of course, generates a stereogenic center. And so we get an equal mixture of addition. Let me go ahead and make one of these a wedge. We get an equal mixture of addition from the top face and the bottom face. So I'll indicate that by writing +E. And of course, if you wanted, you can add a cuprate to this position. So R2CuLi, right? And that would form a bond here at this position. The cuprate would add here to this position. I'm not going to finish that up. I don't have the room there, but you know, there's so many options now. Let me not use the red pen. Let me just show that if we wanted, we could do this same kind of addition now that you've oxidized this to an enone. If we wanted, sorry, I just can't resist drawing this because I feel like, wow, look, we could have also done a 1,4 addition to this enone system at this end carbon if we wanted to do that with a cuprate reagent. Okay. This is the end of our exam 1 material. In about a week and a half, we're going to have an exam on Monday, and it's going to cover chapter 18, electrophilic aromatic substitution. It's going to cover chapter 19, which is the acidity of OHs in phenols and carboxylic acids. You need to know how to draw the conjugate bases with O- and figure out which compounds are most stable, usually based on resonance. Then chapter 20, you have to know every single one of these new tools that we taught you, using organolithium reagents, organomagnesium reagents, hydridoaluminate reagents, hydridoborate reagents, and cuprate reagents. You need to know the distinction between adding to aldehydes and ketones versus adding to esters. So much to learn, and there's so much for you to practice. You've got to practice those tools, because I promise you I'm going to be asking the heck out of all those different types of reactions. So there's so many more reactions in this section.